So this is session 2, and in this session we're not going to do any practical exercises. It's just going to be kind of a more theoretical overview of what medical images are and what segmentation is. By now you should have already ITK-SNAP and Convert3D installed on your laptops. The objectives for this session are to describe the kind of image analysis, or more specifically segmentation problems that ITK-SNAP is suitable for. Describe how medical imaging volumes are represented by ITK-SNAP. List different types of image layers that you can open and view in ITK-SNAP. And also talk about image metadata and how it can be represented and accessed. We'll talk about what is segmentation, what is ITK-SNAP, and then understanding medical images. So what is segmentation? In a simplest sense, it's a process of locating structures of interest in an image and separating them from other structures in the background. So, for example, in computer vision applications, we might want to separate a cow from a field, and there are all kinds of smart algorithms that allow you to do that by just squiggling on top of a cow and squiggling on top of the field. And this is an example of segmentation, a little bit different from what ITK-SNAP does. In medical imaging, the kinds of segmentation problems are a little bit different, and there are two kind of broad categories. On one hand, you have problems where you need to segment all voxels in a particular class. So you have a brain image and you want to label sort of globally throughout the brain image all the white matter, all the gray matter, and all the cerebrospinal fluid, and maybe if you have lesions in the image, also segment out all the lesions. So ITK-SNAP is not, it can sort of address these kind of problems, but it's not the ideal tool for these kinds of problems. It is a better tool for the kind of problem where you have a specific anatomical structure or a specific lesion, specific tumor that you're after. There, this is, for many people, a tool of choice. So it's kind of a more hands-on local segmentation rather than fully automated kind of global partitioning of the image into different classes. The kinds of segmentation techniques that are out there, and there are thousands and thousands and thousands of papers on medical image segmentation, we can categorize them into fully automatic, where we just trust our data to the computer and the computer does everything for us. And then semi-automatic, where the user guides the computer in performing the segmentation. And then there's finally completely manual, where the user actually outlines the structure of interest. And ITK-SNAP is used for these last two kinds of segmentation problems, so semi-automatic and manual. So let's talk about how medical images are represented in a computer in general, and then specifically in ITK-SNAP. So medical images are usually obtained on some kind of a scanner that are then reconstructed to represent it as some kind of a data structure, like a 3D array, three-dimensional array, and then they're stored in an image file. And a medical data image file almost always consists of some kind of a large chunk of data, so a sequence of values representing this three-dimensional structure, and then some metadata, so information about the image. It's not the values themselves, but information about the values, what these values mean. So for example, if these values are 10, 100, 300, what are those values? For CT, those might correspond to Hounsfield units. For ultrasound, they correspond to something else. So that kind of information is encoded in the metadata. Patient information might be encoded in the metadata. The dimensions, the physical dimensions of this array will be encoded in the metadata. So an image volume is a three-dimensional array, like we said, and this is what it might look like. And every cell, every value in that array represents intensity at a particular location. So here we're looking at a little square in the image, and as we're zoomed into it, we see some list of values, and we refer to these cells as voxels. So we're going to use the term voxel to represent one cell in this three-dimensional array, and the value of the array, the 453, we're going to call image intensity. Of course, as humans, we're not very good at visualizing three-dimensional arrays. Our vision is two-dimensional. So there are different techniques that we use in order to visualize three-dimensional data. And two of the more common techniques are slicing and volume rendering. Slicing, you basically take some two-dimensional plane through this three-dimensional array, and that gives you a two-dimensional array, a picture that you can then visualize. And you can move this slide around in space and get different snapshots of the three-dimensional volume. There are also different kinds of techniques, volumetric type techniques. So an example here is volume rendering, where you sort of look at some kind of a surface representation of the data or something different. You might have actually there's three-dimensional data traced to look like a two-dimensional. I mean, you can have depth information, not just surface information. But this is kind of a visually nice way of looking at data, but it doesn't give you as much information about precise values at a precise location as slicing does. So slicing is more limited because you're only looking at kind of one aspect of the image, one plane through the image, but it gives you sort of more complete information than volume rendering. So we're going to be mostly visualizing using slicing. So in ITK-SNAP, we view this three-dimensional volume by slicing it in three orthogonal directions. So we slice it like this, we slice it like this, and we slice it like this. And so whenever we open images in ITK-SNAP, you'll see this kind of configuration on the left, and what you're seeing are axial, coronal, and sagittal slices through your three-dimensional volume. So in addition to the actual intensities, the image contains metadata, and let's see what kind of metadata an image can contain. So we might have subject information, so name, a medical record ID, etc. That's the kind of information we don't want to have laying around on our laptops, because that would violate HIPAA. So it's important to keep an eye, make sure that the images that we work with are anonymized. Scanning parameters, so for example, if you're using MRI, your image metadata might contain TR and TE values. Some information for the computer to know how the image array is actually stored on disk, because three-dimensional arrays in a computer always have to be stored as just a list of values. Computer memory in the end is just a one-dimensional array. And then information about the spatial extent and orientation of the image. So where this three-dimensional array is in relation to the scanner coordinate system. And that's an important bit of information to know. And also, in some imaging modalities, voxel intensity might have some kind of a physical meaning. So for example, in CT, Hounsfield units. So that information can also be encoded in the metadata. So we'll go through a couple of these pieces of metadata in more detail. So for example, one of the things I mentioned is how this three-dimensional array is represented in a computer. And so here we have on the left a picture of three-dimensional array. The computer represents this three-dimensional array as a one-dimensional array. And somehow, when we load an image, we need to know how to traverse, what is the traversal of the three-dimensional array in relation to a one-dimensional array. So are we going column first, or row first, or slice first? So that information, as a user, we don't really care about it. It's kind of transparent to us. But it is important part of what the metadata in an image file contains. More important for us as users is information about spatial orientation. So this three-dimensional array and different directions in this three-dimensional array, so the column direction, the row direction, and the slice direction, they map somehow to directions in the physical space of the scanner. So for example, if the image is acquired axially, then that means that these sort of planes correspond to planes going like this. But if the image is acquired sagittally, then these planes correspond to planes acquired like this. And that information is in the image header, in the image metadata, and it's important when we're using multiple images of the same subject and try to compare them. If that information is not correct, the images might not be lined up correctly. So, for example, in MRI, we might acquire a flare scan axially and a T1 MRI scan sagittally. So, in two different scans from the same MRI session, this encoding of how the directions in the image array map to directions in physical space will be different. And if we don't capture that information, or somehow that information gets corrupted as we're changing image formats, then we're no longer going to be able to correctly line up the T1 scan and the flare scan. So this is kind of showing that every voxel, every location in this three-dimensional array can be mapped to some location in some physical coordinate system, which is defined relative to the scanner. Three-dimensional images are stored in a variety of different file formats. Just like for two-dimensional images, we have PNG, and we have TIFF, and we have JPEG. For three-dimensional images, there's a variety of formats. And different formats store data and metadata in different ways. So there are some formats that we consider recommended because they capture all of the metadata in a consistent and robust way. And some formats that are a little older, perhaps, like the analyze format, that might not capture all of the information and then give us more problems when we work with them. And formats differ by the amount of metadata that they can store. So there are some formats that can only capture very basic metadata, and some formats that can capture very rich metadata. So the format that is most widely used overall is DICOM, because it's a standard format for the scanner industry, and pretty much every medical image scanner in use today generates output in DICOM format. So strength of DICOM is it has a very rich metadata support. So if you look at the DICOM header, it contains hundreds of entries, including information about the patient, the center where the images were acquired, all kinds of scanner parameters, etc., etc. DICOM is also very flexible because it has to be. The same format has to support ultrasound, X-ray, and three-dimensional modalities, and even complex things like time-varying functional MRI or multidirectional diffusion MRI. So it has to be very flexible in terms of the dimensionality of the data, which also makes it a little bit of a hard format to work with. So most of the time, when we get a three-dimensional image in DICOM format, it's actually represented as a sequence of files for each two-dimensional slice. So if you ever get a CD from a scanner and you look at the directory structure, you'll see that there'll be sometimes hundreds, even thousands of files representing different slices in the DICOM image. What also makes DICOM a little hard to work with is that often those images are not named in any kind of a meaningful way. They're just 0092 something. And so you might have two scans from the same session and not really know from looking at the file names where one scan ends and the next scan begins. DICOM is also not very good for storing what I call derived data, basically segmentations, analysis results. So if you want to, if you go through and segment several structures in your image and you want to save that as an image, saving it in a DICOM format is pretty complicated. Or if you get some kind of a probability map, let's say from a functional MRI analysis, you get an activation probability map. Again, storing that in DICOM is very uncommon. So DICOM is kind of a standard for input from the scanner, but then in the analysis pipelines, it's seldom used. So typically, we'll take DICOM images, anonymize them, and then convert them to a different format for analysis. And anonymization is very important because the metadata usually will contain patient HIPAA-protected information, which needs to be removed before we share it with anybody for analysis. I mean, most of our IRB protocols state that DICOM data gets anonymized before anything else happens. So ITK-SNAP can read DICOM and it can convert it to other formats. However, it does not currently do an anonymization. So we recommend using DICOM to NiI or other DICOM converters to convert to the format that we prefer, which is the NiFTI format. So the NiFTI format can be considered sort of the standard, at least in neuroimaging research. And the difference with NiFTI is that it actually represents three-dimensional or even four-dimensional or five-dimensional arrays within a single image file. So you don't have this problem with hundreds of thousands of separate files. It also has fairly limited metadata, which is restricted to the spatial extent and the orientation of the image array. There's a code to represent the intention of the image, so it's an anatomical image, a segmentation, or a statistical map. It does not have any fields for patient identifiers, so you can be pretty sure that if you're working with a NiFTI image, it's anonymized. And it's excellent for storing derived data, like segmentations. It's also understood by most of the modern image analysis tools, like, say, 3D Slicer or MRI Crow or a number of other tools. So it's good for interoperability. And it can also be easily compressed using gzip compression so that you don't have to use up so much space on your disk. So I highly recommend using NiFTI format when you're working with ITK-SNAP. Even though you can load and save a variety of other formats, this is by far the easiest format to work with when you're using ITK-SNAP. But there are other formats, and we support something like 13 of them. And some of the common ones are meta image and analyze, which is a predecessor to NiFTI. And they all have some certain limitations where we find that NiFTI is just a little bit better to use. So we've talked about image formats. Now let's talk a little bit about how segmentations, the results of this segmentation process, are stored and represented in ITK-SNAP. So here's a typical example of a completed segmentation where we have labeled the liver in yellow, and we've labeled bones in green and kidney in red. And the way we represent these segmentations is by assigning every voxel in this image a label. So for example, all the voxels that we believe to be inside of the liver are assigned label 5, which corresponds to the liver. And all the voxels which we labeled as bone, we're assigning them value 2, which is going to correspond to bone. Finally, all the voxels that don't belong to any of these structures, we call them background voxels, and they're assigned the label 0. So the result of this is that every voxel in the anatomical image, every voxel in the CT or MRI, is assigned a unique numerical label which corresponds to a different anatomical structure. So for example, background 2 here might correspond to liver, 5 corresponds 2 to bone, and 5 to liver. This 5 should have been yellow. Missed that one. And so this itself is basically an image, right? This is an image, an anatomical image, an actual scan. This is a segmentation image, what we call a segmentation image. It's a 3-dimensional array, same dimensions as the anatomical image, and it's used to represent a segmentation. So that's an important point to keep in mind as you're working with ITK-SNAP, that segmentations are represented as images. You have an anatomical image, and then you have this segmentation image. When you start working, there is no segmentation. The segmentation is empty, so this image is just full of zeros. Then if you go and start tracing out the liver, let's say, you're basically changing the label of some of those zeros, you're changing some of those zeros into 5s. Then you go label on kidney, the kidney, you're changing some of those zeros and 5s into 1s, and so on. So of course, in order to be able to interpret this data, you need an additional piece of information, which is what these labels map to in anatomical terms. So there's a separate file, which we call a label description file, that describes how the numbers here, 0, 2, and 5, map to anatomical structures. So 0 is always going to be background, but then this file is going to specify that 2 corresponds to bone, and 5 corresponds to liver, and so on and so forth. So in addition to displaying images and segmentations, ITK-SNAP also allows you to display more images, additional images, as overlays on top of your what we call main image. So an example here, so it's a T1 weighted MRI scan, which is shown in grayscale, and overlaid on top is a color map derived from a diffusion MRI scan. And this color map, in this case, represents the principal direction of white matter fibers extracted from this diffusion scan. So, this is good for visualization, but might even be useful for segmentation work. Other kinds of overlays that you might visualize in ITK-SNAP are statistical maps. So, let's say you're doing some kind of analysis outside of ITK-SNAP, computing differences in cortical thickness between patients in two groups. And then you would like to visualize that cortical thickness difference map on top of your some kind of standard anatomical template. You might see this in a lot of neuroimaging papers. So you would load this standard template image, and then on top of it you can overlay this probability map that you generate. Another way in which we use overlays is that if we have different modality MRI scans acquired from the same sessions, so T1 MRI, T2 MRI, flare, diffusion, etc., we can also load them all within the same ITK-SNAP session and work with those different modalities together rather than separately. So logically, ITK-SNAP organizes its images as we think of at the bottom there being the main image, that's your first image that you load. And then there optionally may be additional overlay images like that diffusion MRI direction map. And at the top there's always this segmentation image, this image of 0s, 2s, and 5s that represents the segmentation. So the main image typically will represent anatomy. The overlays will represent other anatomical modalities or analysis results or statistical maps. And the main image and the overlays are read-only. We never really change them in ITK-SNAP. We view them, but we don't change them. The segmentation image is the image to which we make changes. That's the image that we modify and then save. So that concludes the session. Let me just summarize. So ITK-SNAP is best suited for automatic segmentations of structures that have good intensity contrast with their surroundings that have nothing to do with what I talked about. Looks like the summary slide was from a slightly different set of slides. And manual segmentation or touch-up when automatic methods fail. ITK-SNAP represents images and segmentations as three-dimensional arrays, and image metadata describes the organization of the 3D array and relates it to physical scanner, environment, and subject. And ITK-SNAP supports many image formats, but NiFTI is the one that we recommend the most. And finally, ITK-SNAP has 3 types of image layers: main image, overlays, and the segmentation layer.